Science requires testable, repeatable, predictable results as the gold standard proof of any theory. Today I want to present another set of testable, repeatable, predictable results from electric geology as proof that shock waves and supersonic winds formed Earth's mountains during a period when plasma storms raged in the atmosphere. Shock waves, supersonic dusty plasma winds, and how they made non-volcanic mountains and mountain ranges has been examined many times previously, so rinse and repeat. Before we dive into the newest discovery, let's briefly recap the repeatable, testable proofs previously given in several articles, including the shocking truth and when plasma storms engulf the Earth. First, iron meteors were presented as physical proof that shockwave separation bubbles formed tetrahedral dunes. Second, mountain formations were presented as physical proof they are identical in specific detailed form to shockwave separation bubbles and lambda structures. Third, harmonic formations were presented as physical proof they were caused by sonic waves. Fourth, lambda foot or Y-shaped pressure sinks embedded in mountains, a feature particular to a specific region of a shock wave, were also presented. Fifth, Prandtl-Meyer expansion fans, another geometry specific to supersonic winds, were shown to be present in mountains. And sixth, several examples where a variety of features specific to shock waves, including some of the aforementioned and many others, all appear together in mountain ranges in the exact physical context of a supersonic wind formation. All of these were presented with several examples to show they were not just coincidental similarities. They are consistently present features found in mountains around the world. Because of that, supersonic shockwave features are predictable. This is the final tenet of proof according to the scientific method, predictability. I found an opportunity to test the predictability of the shockwave theory, and guess what? It passed. Of course, you'll have to take my word for it that I predicted anything, but when I show the results, that won't matter anyway. The results speak for themselves. This discovery began when I noticed a certain pattern of V-shaped cuts and divots just beneath mountain peaks, always on the leeward side of wind-formed mountains. It didn't appear every time, but only on particularly large and steep mountains shaped by the lambda structure of a shock wave. I first noticed this feature while hiking in the Catalina Mountains, which are my backyard range in southern Arizona. Figures 2A and B show two examples from the Catalinas. Both pictures are of the leeward side at the tip of a tetrahedron, and the feature I refer to are the deep diagonal cuts that bracket the peak and extend downwards to meet, forming a V. I knew these were from shock waves. Shock waves become electrically charged, firstly because they produce such extreme pressure and heat they naturally ionize gases flowing through them, and secondly because they are essentially plasma conduits between the Earth and an electrical storm, so they conduct lightning. As a result, they tend to evacuate any matter that they contact, which leaves sharp geometric cuts in the rock. It was obvious shock waves made these cuts and notches, but I still didn't understand how these particular shock waves formed. Then I discovered the Mach Stem. The Mach Stem is also depicted in the Figure 3 diagram of a shock wave from an airburst nuclear detonation. Because of the particular attitude of an airburst event and the Mach angle the shock wave makes with respect to the ground, it forms a Mach stem at the very tip of the lambda structure triple point. I know that's a mouthful. The detailed technical explanation is much worse. But if you have the interest, this paper explains it. The paper is titled Validation of the Mach Stem Triple Point Film Scanning and Reanalysis Project, dated September 11, 2020, by Jason R. Johnson-Yershak at Lawrence Livermore National Laboratory. I quote one relevant paragraph that discusses why a Mach stem only forms in certain conditions, which explains why I didn't always see the V-cuts on every mountain. Quote, according to Kinney and Graham's research on explosive shocks in air, dated 2014, if the height of burst is increased past a certain limit, only regular and single Mach shockwave reflections can occur at the ideal angle of shock from 40 to 46 degrees. The reflected angle catches up with the incident angle, forming the Mach stem, as the shock wave transitions from regular reflection to single Mach reflection. A minimum Mach number of approximately 1.2 is necessary for the Mach stem to form, while the absolute minimum angle of shock for transition is 39.23 degrees. Unquote. What that's saying is that the Mach stem only forms when the shock wave is at a particularly steep attitude and the Mach number is above a certain value. Also, the Mach stem is a destabilizing effect, causing destructive interference as the shock wave goes through a transitory phase. Very similar conditions apply to certain mountains, especially the very biggest ones. The angles referenced in the quote don't necessarily apply, since the conditions in a dusty plasma would be different, and the source of the shock wave, being a supersonic wind, is much different. But it's still appropriate to form a Mach stem. Therefore, it dawned on me that I should look for Mach stems on Earth's largest and most famous mountains. Mind you, it cannot be just any old V-shaped feature. It must be attached directly to the peak itself, made of nearly straight diagonal cuts that are typically slightly deeper on one side. I think this is because the Mach stem is made from the incident shock and its reflection, and the reflection lags in strength and timing to the incident wave, which will cause some asymmetry. Otherwise, the reflected angle is a complementary angle to the incident wave. Also, the Mach stem will sometimes flatten or break off the tip of the lambda structure, leaving a squared off or double top mountain. This is because the Mach stem is destructive interference, as I mentioned before, caused by instability and interference between supersonic and this small region of subsonic winds at the triple point. You'll also note on close inspection, I show the Jungfrau mountain, that there are sometimes triangular harmonic shock reflections embedded within the V-notch. They're not always present, but not uncommon either. They're often covered by snow. I began my search with the famous Eiger in the Alps. The death wall, as it's known by climbers, is the near vertical wall on the north face of the mountain. This is the leeward side. The other side of the Eiger is a steeply sloping triangular face that forms the windward, or what we call the ski slope side. Climbers, of course, take the steeper north wall because it's the most likely to kill them, and so it has several times. That's why it's called the death wall. Those who succeed, however, do so by climbing the final pyramid through the exit cracks, which are diagonal cuts in the rocks in a V-shaped notch just below the mountain peak. That notch is the indelible imprint of a Mach stem. Then I looked at the north face of the Jungfrau. It's the mountain right next to the Eiger, and it too has a V-notch. Well, in all honesty, I already knew I'd find a notch on the Eiger. I was aware of the climbing history of the mountain, and the fact climbers use these diagonal cuts and the V-notch as part of the standard route. But I predicted that I would find the same thing in the Himalayas, and each of these has a V-notch. As you can see, there's a V-notch created by a Mach stem on a baker's half dozen of the tallest, most famous mountains on Earth. There isn't much else to say. Believe your lying eyes or believe the consensus explanation if you can find one. Typically, this is the kind of thing they dismiss as another marvel of nature, a coincidence. But now it has an actual name, with data and calculations that describe its physics, the Mach stem. But wait a minute, could the limestone of the Himalayas, Karakoram, and the Alps have some kind of preferential angle of fracture that erosion inevitably produces at the tip of limestone peaks? Surely this is some characteristic of the rock, plus a million or so years of erosion, the way everything else happens, according to the consensus, right? So I looked in the Rockies, which are granite, and the Andes, which are primarily granite too, and lo and behold, they have V notches and diagonal cuts at their peaks. In fact, you can't turn around without seeing a V notch. So that leaves the type of rock, not the cause. It must be shockwave. It can't be anything else. The standard explanations of fracture planes and erosion do not hold up under scrutiny. The Mach Stem is at the very peak of the mountain, exactly where it belongs on a shock wave, and where there is no watershed to collect water to erode anything. Ice will certainly fracture and erode rock in freeze-thaw cycles, but ice isn't guided by intelligent design. These are consistent features of geometric certainty with opposing complementary angles that always conspire to be in the same place, same arrangement. Also, the V-notch is always on the downwind side of the largest, steepest lambda structure mountains that show no such freeze-thaw erosion on the windward side. The windward side is generally a smooth planar face with no notches. Mountains with the large lambda structure geometry display Mach stems regardless of rock type, including shales, limestones, and granites. I'm nicknaming it the seat of Olympus. It has a nice ring to it, and it certainly fits, being kind of like a seat at the peak of the tallest mountains. For good measure, there are some more examples, and each of these has a missing or damaged peak due to destructive interference from the Mach stem. Also notice how similarly the notch leaves a half-moon hollow between two peaks in each case, another marvel of nature. And one final image, I've highlighted the Mach stem. As a seat for Olympus, it looks a bit uncomfortable, but that is a very interesting thing because it is spiked with harmonic reflections. The entire lambda structure must have been vibrating when this mountain formed to produce these harmonics. The interesting thing is the size of harmonic reflections inside the highlighted Mach stem are all of a size significantly smaller than the harmonic reflections outside of the Mach stem. That's just one more proof they were produced by sonic waves, and that the Mach stem rings to its own frequency. In summary, we can add another proof of theory to a growing list of proofs that supersonic winds and shock waves shape the mountains. Mach stems are a repeatable shockwave phenomena that appear only at the shockwave triple point on the windward side of mountains formed by a lambda structure. That is a very specific thing, and it's reproducible and predictable. The lambda structure's geometry and dimensions and the existence of a Mach stem provides a wealth of information that would increase our knowledge of Earth's formation. It can be used to estimate the Mach speed of the wind when the mountain formed, what direction the wind was blowing, and what dust was born in the plasma wind since it left deposits. Re-examining the wealth of geologic data available in its proper context, knowing plasma winds and Jupiter-like storms played a significant role in shaping the landscape, would allow us to reconsider the sequence of catastrophic events that created the Earth's stratigraphy and fossil record, and perhaps understand the cause. I got a lot of satisfaction when I'm inspired by a moment of aha, to find my crazy idea turns out to be true. Discovering the Mach stem is especially sweet because the Mach stems are so prevalent and easy to spot, anyone will see them and think of shock waves, whether they want to or not. Like the Mach stem, ring to your own frequency, but don't be a destructive chip off the old block. Resonate with goodness, gratitude, and Mother Earth.